All right, the last second order process I want to talk about is called the electro-optic effect. In the electro-optic effect, we see that a static electric field can change the index of refraction of a crystal if it has a second order nonlinear susceptibility. Here, let's take a look. So the situation looks like this. We have an incident electromagnetic wave at frequency E of omega. And then we have a static electric field at frequency 0. And then these are going to be mixed together in the crystal that has a non-zero chi2. And the result will be is that it's as if the index of refraction of the crystal had its original value plus a small term that's proportional to electric field. Okay? And this electric field dependence of the index of refraction, it's a small effect, but it can be used to make some really interesting devices like ultra-fast optical shutters and modulators. And one of the experiments that one group will do will explore the electro-optic effect. Here, hang on. Okay, so in the electro-optic effect can be seen as a special case of sum and difference frequency mixing, where omega 1 is just the frequency of the incident wave, and omega 2 will make 0 for DC, okay? Then we can see, going back to the expression that we just looked at a moment ago, we can get the following result, okay? Oh, I'm sorry, 1 second. I'm just neaten things up. Okay, so now the nonlinear polarization will be equal to equal to the this E0 times chi2 times the electric field squared, where the electric field is the sum of the DC field and the oscillating field. And this will be E0 chi2 times E0 squared plus E omega cosine omega t squared plus the new term, which is 2 E omega E0 times cosine of omega t. There we are, okay? And now that means that the nonlinear polarization can be written in a series of terms. There's a DC term. There would be a second harmonic term, but we're not really interested in that today. But there's also a term at frequency omega, which is this term here. So it oscillates at the same frequency as the incident light wave, okay? And now let's see why that third term is important. The reason it's important is that that term combined with the linear term acts like this term produces a change in the index of refraction. Let's see how this works. Let's look at the total polarization at frequency omega. Okay? So the total polarization at frequency omega will be given by epsilon 0 times the, I'm sorry, let me rewrite this. It'll be given by the linear polarization, that's epsilon 0 times the electric susceptibility times E omega, plus this second term, 2 epsilon 0 chi 2 times E0 times E omega, okay? Or if we like, we can write this as E0 times chi, electric susceptibility, plus 2 chi 2 E0 times the electric field of frequency omega. And the reason to write it this way is that then we can see that the term in parentheses looks like a new linear electric susceptibility. It contains the actual linear electric susceptibility plus another term, but the second term is proportional to the static electric field. And that's why the index of refraction changes, because the electric susceptibility changes with electric field. Here, just to finish this off, the term in brackets then, we can interpret it as being the dielectric constant of the material minus 1, okay? And that means that the new dielectric constant of the material is given by the old dielectric constant plus this term. Oh, I'm sorry, excuse me. That shouldn't be there. Okay, let me just rewrite that. Okay, very good. And then the index of refraction, which for a non-magnetic material is just the square root of the dielectric constant. That's just the square root. I'm sorry. Yes, we can write that like this. Okay. And we do that for the following reason. Oh, just let me neaten this up, and then I'll tell you why this is so beautiful and important. There we go. We can rewrite that like this. And now we can see that that because the second order polarization is just a small correction on the linear polarization, this term here must be much smaller than 1. And because of that, we can expand the square root in a Taylor series and just keep the first order correction. We can rewrite this in the following way. So the square root of the linear dielectric constant, we can write as N0 squared. And then we can write this as 1 plus 2 times chi 2 E0 divided by, well, actually, again, N0 squared. Okay? The 2's cancel, and we're left with our result. Oh, excuse me again. There we are. That shouldn't have been squared. Then finally, we have the new dielectric constant is the old dielectric constant plus a second term, okay? I'll call delta N, where delta N is just chi 2 E0 over the original dielectric constant squared, okay? And so it's proportional to the static electric field. Okay, very good. So what we've shown is that in electro-optic materials, we also can have the electro-optic effect, where a static electric field can change the index of refraction of the material a little bit. And this is important because in many cases, we can use the index of refraction to control a beam of light. And so the ability to slightly vary it allows us to make things like optical modulators and optical shutters based on the linear electro-optic effect. All right, let's stop here with this one, okay? Very good. And we're gonna go on now to talk about a third order nonlinear optical effect, and then we'll be done.